So yeah, so today we're going to effectively repeat a lecture that we had also done in the basic course, but which I will really push out to just this course because there's so much material in the other one. But so we're going to repeat this, and I'd like you to really understand what's going on, because in your lab you are going to, create a library for write and read data from and to your SRAM. So how are we going to do this? So let's first get a higher level overview of what's going on. Well, you have your CPU or MCU, and you have address lines with which you can address all kinds of external, memory devices. I sort of like to think of the other devices that also are part of your I/O as also memory. In a way, it is. I mean, I'm addressing. Well, if I take it to its most generality, I'm sending an internet packet over to an IP address, right? That IP address can be thought of as a physical location of some storage or something. So I try to abstract quite the heck out of it, but if you think about it like that, then you can realize that you have addresses that uniquely identify within this memory even separate blocks or pages or other types of segmentation that you have done. And those physical addresses also uniquely direct you to the to other devices that you may want to communicate with. So effectively, you want to transmit an address to indicate what you're interested in, where should the data go to, or where do you read it then from. And of course you have a control line to indicate to the devices with whom you are actually communicating. So this is a very basic type of structure, but what we'll see is you cannot sort of have unique address lines for the memory and unique address lines for the other devices. So your control line says, okay, I want to talk to you here. Well, let me then use pins, B1 to B8 or something like that. No, you want to make use of all those lines for all of your devices and memory, right? So you want to use the address lines not just to communicate to this memory, but also to the other devices. So you want a so that's what creates a parallel bus interface. Now, let's have a thought about what memory, how we're really thinking about it. So effectively think about it as values, data that are addressed by certain physical locations that have identifiers that are, for example, 16 bits. Now, if you have 16 bits, means that you have 2 to the power 16 addresses, and say each address location can store 1 byte, then I would have something of this form. 64 is 2 to the power 6. The K of kilo is 2 to the power 10. So I have 2 to the power 16 bytes. And similarly for 32 bits I would have 4 gigabytes. And I can choose in my memory to have what we call a flat address space, meaning that all the bytes are really in your physical space are really addressed by physical addresses that are also the logical addresses. So we're separating out logical and physical addresses here. So the physical addresses are really the ones that your device is using, while the logical addresses are the ones that your operating system is working with. That's how you could think of it. So there will be a translation from logical to physical addresses, but if you use a linear address space, there is no such translation. It's just a one-to-one mapping. But for example, if we have pages, say, so like that's what your laptop is doing. So you segment, say, your DRAM into pages, then you have a address to a page, and that is sort of a continuous sequence. And then within an address, you may have within a page, you will have what we call cache lines, for example, right? Cache blocks. And within a cache blocks, you would have, say, 6 separate, well, if you have, say, 32-bit processor, say 32 bits separate blocks, things like that. So, how do you deal with this? Well, you need to sort of understand from the logical address where you need to go in the physical space, and that's what we call address translation. And that we don't really care about here. It's all about making sure that within our limited system, we understand how we translate our logical to the physical address space. All right. So if we have in our MCU, we have two kinds of memory. We have program memory, we have data memory. Remember that the program memory actually stores your instructions, and it persists over turning off and on your device. And we also maybe you remember that we could also, if we include a specific type of library, we can actually make use of the program memory to also store some data that would then persist over turning off your MCU. But effectively, the data memory that so the memory that's used for data, called the data memory, has a whole bunch of information. There's the first 32 registers. Remember, those have the addresses for where to jump to in case of, say, an interrupt. So you have an interrupt, you look up which interrupt it is, and there's an address that then makes you jump, or the MCU is jumping to the interrupt service routine that is that is located somewhere here, that will then execute. Now, clearly, if your MCU is starting to bootstrap, it will initialize. It will start to fill those registers with information and stuff like that. So you could do, and so forth. You have some I/O registers, other kinds of stuff, and you have some internal SRAM reserved for your MCU for its general operations, and then you have a block of SRAM that you are allowed to use. So this is how that would work when we're thinking about the address space, and that is it. So if you come to interface external SRAM to the Atmega, we are going to keep some internal memory separate. That's how we usually do it. We have a bunch of lower and upper sectors and so forth. But the point is that you need to address this memory. So you have address lines. And you also want to write data to the memory or read data from it. And what you will do is you will multiplex pins, lines, for both transmitting address information as well as transmitting or receiving data. So that's why we call this A and D. Is both used for address and for data. And you have a whole bunch of other lines that are purely for the addresses, as an example, right? So for example, we have here 16 bits indicating an address. So we have A0 up to A15. And we have also, we can write a byte from D0 to D7. Now and then, because of that, you will have a ledge that will first, be used to indicate that you're going to use those lines for address information. That's how you can think of it. So you have an address ledge enable, and then later on you want to do the reading of data over those pins, or you want to do the writing. And so you have the general lines, the RD and the WR, that are connected to your SRAM, that are control lines that will effectively tell the SRAM in what kind of functionality it must operate. So, like reading or writing. Alright, so this is the picture then. we have these lines that are multiplexed and both used for address for data as well as for addresses, and this is effectively what I just told you. So this is the picture, and actually you're going to create a picture like that. So when we go forward in the slides at some point, you will see again a layout in which you are going to create something like that to connect to your own SRAM. So if you look at the usual way of dealing with this kind of stuff, so again, this is in the data sheet, by the way, right? So you can look at your ATmega. So here we have ATmega 162, but the 328 is doing the same thing. So you can look at the data sheet and you will see a picture like this, and it tells you how to operate an SRAM. And here it is. So you have your usual system clock. You will have the latch enable, address latch enable. You are having all the address bits coming in. There was a previous address that was sent, and now you will send a new one over here. So it is indicated by this, so new address. Great. If we're looking at data pins, you would see that after the previous data, you would actually, so the address has, how you say that? So the address is written during this period, so the address is there, and then at some point you are going to write the data. So you indicate through the write when that should happen, when the data is available, so you have communicated address information over. So effectively, if you look at those pins, you have address information coming over, and now you got indicated by this write control line, you will see the data appearing. And for a read, it's a similar thing, right? So you would now receive data over these lines. So it's pretty much the same story. The point is just, all that you need to remember is that you need to operate those control lines properly, and the latch as well, and it all needs to be separated in time in proper ways. But that may be a problem actually, because normally your MCU is way faster. So how do you make sure, then the peripheral, say in this case your SRAM, so how can you make sure that they are synchronized? So what you want to do is, the peripheral devices may not be able to respond to the processor requests within the next clock state. So effectively the data on the bus may be invalid when they are read by the processor. And why is that? Because effectively the processor is doing this at a much faster pace, right? So it expects to see the data, but the peripheral was not yet ready and did not output the data yet. So the data lines simply do not have that information yet. So that's why you need to introduce wait states. So you inject one or a couple more extra clock cycles in the bus cycle just to make sure it all works. And for asynchronous processors you can work with acknowledgement signals and all that. So here we have the same picture again from the data sheet, by the way. And you will just introduce a couple extra clock cycles that are called the wait state, so that you effectively are waiting as a processor for the peripheral to be finally ready, if you can, if you say like that, to have the data on the data lines, and also have read so when all of that is synchronized. Okay, so in our case, right? Suppose we want to have a bunch of devices. So think of devices as being external memory again. So they're addressed. You assign addresses to those devices of yours, to your peripheral devices, and so the address bus indicates effectively with whom you want to communicate. So when we, for example, often think, say in those communication protocols, you have a master and a whole bunch of slaves. Well, you indicate with that control line which slave you would like to communicate to. So in that case, you can say it is one control line, and you use it to transmit like 8 bits of address information for the possible 2 to the power 8 slaves. So in a way you can think of that as being a multiplexed address line. One single line with 8 bits of address information for that master-slave communication. So it's ultimately parallelized, if you will. But what you need to do is you need to use an address decoder. Now in this particular case, the address decoder in a master-slave configuration, the slaves will have that decoder at their own ends, and they will then decode whether the transmitted 8 bits over that line indicates them or not. Now in our case, here it's a little bit different. So you have a general address decoding logic that is then going to have separate lines per device, and it decides which of those devices will now get enabled. That's effectively what this is. But again, it's an address decoding logic, and in our case we will also transmit address information over, like say 16 bits if you have an SRAM, or in other examples that we come up with it's a little bit different. So that is sort of how you can think of the big picture. Now if you're going to look at the following problem, which I had explained also before, so you may have seen it already, but I like to do it again because it really explains what's going on. Say you have one SRAM with 32K, and you have another, say, 3 devices grouped in 3 8-bit latches that each drive, each latch drives 8 LEDs, so you have 24 LEDs. And we want to create a map address decoder. Now we'll use partial decoding. So what does that mean? It means that we're not going to use all the 16 bits in our decoding logic to precisely indicate which particular device I'm interested in. What could I do? I could indeed say the 16-bit number 0 or something like that, or whatever, 100 indicates the first latch. 101 indicates the second latch, 102 indicates the third latch, and then the rest of the bits we will have the rest of the possible addresses are for the SRAM. But that would mean that you would need to look at all of your 16 bits, and then based on all of those 16 bits decide which device you're connecting to. So what you want to do is you want to make sure that that you do this in a more efficient way. So why not just have, say, the first 3 bits, the most significant 3 bits, indicate which device you are going to communicate to? Now why would I be able to do that? Well, effectively what I'm going to do is I'm going to assign a whole address range to latch 0. In other words, all of these addresses, these logical addresses in this range, will, if I use one of them, doesn't matter which one, will be directed to that latch 0. And here we do the same, and here the same. And then we have for SRAM we have a nice huge range that is 32 kilobyte, actually it should be kilobyte, right? So 32K number of addresses. So yes, have a look here. So why is that the case? Well, we have so we always start with an 8, and then we have which is wait a minute, is that correct? Yeah, of course. With this particular number, and so if you count how many possibilities there are in this address range, you will figure out that 32K easily maps in there. Alright, so how are we going to do this then? So let's look at the next picture that shows it again, but now maybe a little bit better. Effectively, if you're going to write out the types of addresses that map to the internal unused space and the space that goes to the latch 0 and that part goes to latch 1 and so forth, you will see that I only need to look at the A15, A14 and A13 bits to figure out which latch I'm interested in and whether I go to SRAM or not. So it's a very simple decoding logic. I'm going to have a look at A15 to indicate whether I go to SRAM or not. If I do not go to SRAM, I will enable this, and then I'm going to look at A13 and 14, which gives me 2 bits of information, which are 00011011, and that gives me 4 output lines. The 011011 inputs are connected to latch 0, latch 1, and latch 2. So that's the decoding logic in this particular case. So that would lead to this complex picture, but again, it looks pretty much similar though. We have our decoding logic over here, which needs just the A15 to A13. Then it can decide whether it goes to latch 0, latch 1, or latch 2, or to SRAM. All of those will receive where's the data? Oh, here. So we have a multiplex bus again with a latch. So that means that we are multiplexing these pins for both data and addresses. So we see that these pins are the higher order address bits, the most significant ones, and here we have the lower order one. They are all coming together, so we have A0 to A15, and they are essentially in a general type of structure. They would all be read by all of these. Now, in this specific example, the latch 0 is just one single device, so we're only essentially having one. All of these addresses, they're not even hooked up with this latch because it's driving a LED. But generally, it could be another piece of, it could be another type of device that actually would need that information. So all of these address pins ideally would actually be connected to all of this. So if I'm enabling the SRAM, then obviously I'm going to read all those address lines. And once it expects the data coming in or writing it in, then we will use this particular line, and you will have this multiplex. So you have given the address latch enable line is only used, is indicating whether you use this for an address, for addresses or not. So in this case not, so then you would use it for the data. So this is sort of the structure. Now in this particular example, just for completeness, how would you connect the LED latches? So you are only interested in the data. You're not interested in connecting the address lines, right? That this picture actually suggests, but in this example we don't. So you use another latch to store your data that drives continuously these LEDs, and the LEDs will now shine the bit sequence, the 8 bits. And when I'm going to override it, then I have used the address decoder. Tells that particular latch that now it should expect data effectively, and it will be overwritten, and then you have effectively a write. You have created a write procedure that can write to the latch, and that's how you can think of it as being memory too, right? There's a write procedure. And we don't care about reading in this particular case because we're just showing a light pattern. So, is this clear, this part? So this is kind of important. So this gives you the structure of how these types of mappings work. Now we can go, let's be a little bit, let's give a more complete story. So we're talking about the translation between logical and physical memory space, and we just did that in hardware with decoder logic. In your computer, you actually have hardware which does the logic to physical address translation, and it's actually quite time-consuming in a way, and it's a bottleneck in your CPU. So that's why a lot of research effort, lots of engineering effort has been put into making that little module in your CPU as fast as possible. So it can process a high throughput of address requests. Now, Memory management unit handles this address translation, so that is what that module can be called. And and we have a couple of possibilities. The physical memory can be larger than a logical memory, and that's what we call banked memory. You can then divide the physical memory in n partitions, and each partition is then effectively indicated by that by a logical address. You got physical memory can also be less than your logical memory, in which case, well, you want to store much more, but it's not as much memory. That's where we are sort of thinking about virtual memory. And that means that you need secondary storage that will store all of that for you. So in your computer, you would have a disk. So you would have, first you try your internal cache to see whether the data is in there. Then you will try the DRAM and load it into the cache. But say it's not in your DRAM, well, then you need to do on-demand loading, meaning on-demand paging from the disk into the DRAM. So then you need to evict something from your DRAM to the disk, or usually you just throw it out because you've already you handle that properly, and then you can bring into DRAM what you need. But you still work with this logical memory space, and that logical memory space is oblivious to where exactly the data corresponding to a logical address is being stored. It can be in your physical memory, like the DRAM, that is too small for it, or it can be on disk. And actually it's being managed by internal algorithms in your processor to make sure that that all is handled properly. So you may want to think about protection of memory regions. So you may want to make sure that you use encryption, that kind of stuff. And